Hi everyone, I am Nuria and I am a PhD candidate at the ARTSI lab where we integrate tissue-responsive biomaterials into the medicine field. And today I am very honored to present one of these projects to you. So over the years, hypodermic needles have been the preferred device to administer drugs. One wonders why, since they are invasive, painful, they need to be handled by medical professionals, and let's be honest, who isn't afraid of them? For this reason, scientists, we have been working to develop potential replacements for these scary devices, and our best shots so far have been microneedles. Microneedles are a medical device that contains hundreds of microscopic needles capable of piercing the most outer layers of the skin. Microneedles can be self-administered, like in a Band-Aid, and they are not painful because they do not reach nervous terminations. Microneedles were originally designed to deliver different types of drugs, but in recent years, microneedles have also been proposed as a diagnostic tool because they can extract interstitial fluid. Interstitial fluid is a tissue that is very rich in immune cells and other soluble biomarkers. So if we sample it, it can give us information on the patient's health, just like a blood test. Inspired by the research performed at the Institute, our group has developed a microneedle platform that integrates a therapeutic and a diagnostic arm within the same patch to treat cancer. Specifically, we delivered an immunostimulatory drug that awaits the fighter cells of the immune system to fight the tumoral ones. Simultaneously, the immune cells that surround the tumors can penetrate inside the microneedles. So once we recover the microneedle patch, we can analyze the composition of the interstitial fluid that has infiltrated. This platform works as a non-invasive biopsy. So depending on the cell populations and biomarkers that we identify, we can know whether our drug is working and if we indeed awake the immune system to fight the tumors. So we took our winning picture during one of the first experiments of this project, when we were struggling to design a new and unique biomaterial that could be used to fabricate the microneedles. For us, this was the challenge of the project, because the microneedles had to be strong enough to penetrate the skin and release the therapy, but at the same time, they had to provide this nice and cozy place for cells to flow inside. To meet this diagnostic goal, we had to design microneedles that could be entirely disintegrated, but only after retrieving them from the patient. Once out of the body, we would dissolve them and analyze their contents. Engineering the microneedles so they would have this on-demand degradation feature was really challenging because we had to ensure that the disintegration process wouldn't damage the cells. Otherwise, this could have biased our readout. Finally, we had our eureka moment, and we identified a top polymer. We included in the structure of this biomaterial what could be defined as a chemical switch. So when we turn it on with a reagent, we can dissolve all the microneedle in less than 5 minutes and analyze the different cellular populations and soluble biomarkers that are entrapped inside. We confirmed that our therapy was really effective because we saw a shift in the balance of fighter cells versus the disarmed ones. Our results confirmed that the number of fighter cells increased, and this was accompanied by a dramatic shrinkage of the tumor size. We are very excited because this device could be a revolutionary tool for clinicians, since these microneedles can deliver a therapy against cancer in a non-painful way and simultaneously provide a readout in real time of the patient's state to inform on whether the therapy is working before the disease reaches an irreversible state. Last but not least, I'd like to thank my advisor, Professor Artzi, and all my colleagues and friends from the lab for all the support and help during this fun month. Thank you, everyone, and thank you all who joined tonight.